నమస్కారం. డాక్టర్ బిఆర్ అంబేద్కర్ సార్వత్రిక విశ్వవిద్యాలయం విద్యార్థులకు స్వాగతం. ఈ ప్రసారంలో
Hello students, we are going to have a video lesson on Lagrange's equations of motion and their applications. We see in the monitor the photograph of Joseph Louis Lagrange, and here the Lagrange's equations are not totally new, they are being derived from Newton's laws of motion. Here we will try to see in this chart the formalisms between comparison between Newtonian as well as Lagrangian formalisms. The Newtonian formalism demands the forces to be taken into account are all the forces including external as well as internal forces, whereas in the case of Lagrangian formalism we will try to ignore the forces of constraints using generalized coordinates. We will take only active forces into consideration. There are other comparisons between Newtonian and Lagrangian. They are momentum and force approach given by Newtonian formalism is demanded in the Newtonian system because it is a vector quantity, whereas the Lagrangian equations are dependent on a scalar potential called a energy potential. Work energy approach is there in the Lagrangian one. The Newtonian one is applicable to both conservative as well as non-conservative systems, whereas the Lagrangian approach gives only conservative forces, that is essentially, whereas there are certain things called velocity dependent potentials, they are also being explained using them. Having compared these two formalisms, let us try to see the Lagrangian one. There is a need for what is called generalized coordinates. These generalized coordinates Lagrange calls it as q1, q2, q3 etc. q3n. Here 3n comes because 3 degrees of freedom x direction, y direction and z direction. q3n is equal to q3n as a function of x1, y1, z1, x2, y2, z2 etc. xn, yn, zn and is also dependent on t. For a system of n particles, this is the thing. q1, q2, q3, these q's are generalized coordinates. These generalized coordinates are need not be a particular thing like in the case of Newtonian one. They can be any quantities. For example, they can be positional quantity, they can be position variation with the time called velocity quantity, they can be velocity multiplied by the mass called momentum quantity. This momentum, if it is varying with an angle, it can be an angle quantity or angular momentum. Like that we can take any of these quantities. Now conversely, these generalized coordinates will become as x1 is equal to x1 function of q1, q2, q3 etc. q3n and also as a function of time. Like that we will have all these coordinates as shown in the monitor. Zn is equal to Zn as a function of q1, q2, q3 etc. q3n as a function of time also. So this is how Lagrange introduced the coordinates. For a system of n particles moving independently of each other, number of degrees of freedom is 3n. So like that these large number of degrees of freedom will help us to try to understand the equations. Now, we try to introduce what is called a restriction of the motion. There are two types of restrictions. A restriction of a motion is called constraint as far as physics is concerned. Constraint is the restriction imposed on the motion of the system. There are two types of constraints. One is holonomic constraint, the other one is non-holonomic constraint. Holonomic constraints are the conditions of constraint as equations connecting coordinates and time given as the function of f of r1, r2, r3 etc. rn and t, that function is equal to 0. Here r1, r2, r3 are the distances of all the particles of the system, t is the time. You can take it example as the distance between any two particles of a body that remains constant during the motion. A rigid body has got its fixed distances of the particles of the rigid body, that is not going to change it. So, this is the constraint. They are integrable constraints. This is another important condition for holonomic constraint. Now, we will try to see non-holonomic constraint. The coordinates are restricted either by non-integrable differentials. Example, gas molecules in a spherical container of radius r, if r(i) is the ith particle distance position vector, it can be written as xi square plus yi square plus zi square is less than or equal to radius of that square if origin is at the center of the sphere. That means, the equation has got some inequality. Whenever there is an inequality or a non-integrable differential, it is called non-holonomic constraint. Now, let us try to consider an imagined infinitesimal instantaneous displacement which is consistent with the constraints is called as virtual displacement called delta Ri. If I is the ith particle, its virtual displacement is delta Ri. Now, the total work done by external forces in a system of particles, if virtual displacement are made, gives virtual work. That means, all these system of particles, all of them will give virtual displacements and the associated total amount of virtual work done is 0. Now, take the case of a ith particle, and force acting on the ith particle is external one, hence we call it as FEI, that will be equal to rate of change of momentum, that is P dot I, or FEI minus P dot I is equal to 0. This P dot I is also called as reverse effective force. This leads to what is called equilibrium. Using this, D'Alembert developed a principle that is called as sigma of FEI minus P dot I into brackets delta Ri is equal to 0. That means, virtual work done by the applied forces plus the reverse effective force is taken to be 0. Using the concepts of D'Alembert's principle of virtual work, infinitesimal displacement of generalized coordinates, conservative external forces, Lagrange introduced a scalar which is energy function, and it is as L as a function of q comma q dot comma t is less than or equal to kinetic energy as a function of q comma q dot comma t minus potential energy which is a function of q, that is the position. Using these concepts, Lagrange developed the equations as d by dt of dou L by dou x dot j minus dou L by dou x j is equal to m x double dot plus k x is equal to 0. Here j is equal to 1, 2, 3 etc. n, where n is number of generalized equations of motion that are generated. One of the applications of Lagrange's equations of motion is simple pendulum. Here in this case, this is the length of the thread L taken to be the length of the simple pendulum. This is the pendulum bob. It is making an angle theta at the vertex. So, while it is oscillating in x and y plane, and z axis does not have any coordinates. So, using holonomic constraints, z is equal to 0 and x square plus y square is equal to L square. Now, we will write equations. X is equal to L cos theta, we will take x dot variation with temperature with time minus L theta dot sin theta, y is equal to L sin theta. So, y dot will be equal to L theta dot sin theta. Therefore, kinetic energy is given as half multiplied by m multiplied by x dot square minus y dot square. This is equal to half m L square theta dot square. Now, potential energy is dependent on the function x, hence P E is equal to minus m g into x, that is equal to minus m g L cos theta. Lagrangian now becomes L equal to L function of theta theta dot, because it is dependent on the theta and variation of theta with the time also, that is equal to kinetic energy minus potential energy. So, L is equal to half multiplied by m L square theta dot square plus m g L cos theta. Dou L by dou theta dot is equal to m L square theta dot, and dou L by dou theta is equal to minus m g L sin theta. Hence, Lagrange's equations of motion is written as d by dt of m L square theta dot minus brackets minus m g L sin theta, that is equal to 0. This is written as theta double dot plus g by L sin theta is equal to 0. That is the equation of motion for simple pendulum. Now, we will apply Lagrange's equations to linear harmonic oscillator. What we are seeing in the monitor is a linear harmonic oscillator. Here we have 3 representative spherical balls in which we will observe the oscillations. For this system, we are trying to develop the Lagrange's equations. The kinetic energy of this particular system is taken as half m x dot square, where x dot is variation of the distance x along the x axis, variation with time. Potential energy is given as minus integral f dot dx. Potential energy is minus integral minus kx dx, because f is proportional to minus x. Here the potential energy is calculated to be 1 by 2 kx square plus an integration constant c. If equilibrium position is the reference for our observation, then the potential V is equal to 0 and x is equal to 0 and c also will become 0. Now, the Lagrangian is L equal to half m x dot square minus half k x square. Dou L by dou x dot is equal to m x dot and dou L by dou x is equal to minus k x and now the Lagrange's equation is given by m x double dot plus k x, this is equal to 0, and it is also equal to x double dot plus k by m multiplied by x, that is equal to 0. This can also be written as x double dot plus omega square x is equal to 0, where omega is angular velocity of the vibrating linear harmonic oscillator. Lagrange's equations are now applied to a mass capital M suspended from a spring of mass small m. Here we will be able to see the spring to which the mass is suspended. The mass suspended is made to move like this, so that spring is kept into oscillations, and such a thing you can also see in a toy shop like thing, a plastic colorful spring. Now, while it is oscillating, we will have total length of the spring is capital L, and x is the distance from the ceiling, that is this end, to the concerned point. Velocity x dot is 0 when x is at 0, and x dot is maximum when it is x at maximum, the other end, one end and the other end. Rho, if it is taken as mass per unit length of the spring, and t is the distance of the spring for a small element dt. This is a small element, for example, this is taken to be a small element dt. So, using this dt, the total t, that is the distance for a given small part, is evaluated, and finally, we will be getting our Lagrange's equation. Now, try to calculate kinetic energy of the element dt. This is small element dt which we have taken already, and such thing you can also see in this particular spring. That kinetic energy of the element is equal to half rho into dt into brackets T by L into x dot whole square. Total kinetic energy is considered to be an integration of this over the entire length, half, that means the small dt amount from there to this entire all such dt's put together, it will be a integration, half of integration 0 to L rho into dt into brackets t square by L square into x dot square. X dot is the velocity. This is found to be m multiplied by x dot square divided by 6. Now, the kinetic energy of the system is equal to m x dot square divided by 6 plus half capital M x dot square. Potential energy of the system is dependent on distance and the force constant or spring constant, that is equal to half k x square, where k is the spring constant. Now, we will try to evaluate the Lagrangian of this particular spring and mass system. L is found to be is equal to m x dot square divided by 6 plus half capital M x dot square minus half k x square is equal to 0. Now, Lagrange's equation is m by 3 plus capital M x double dot plus k x is equal to 0. This is simple harmonic in principle, and its period is 2 pi into brackets, within the brackets m by small m by 3 plus capital M, that divide whole thing divided by k to the power of half, that means it is under root of this. This is the time period of the oscillating spring having mass small m and suspended by a mass capital M at the base of this. We will try to see yet another application of Lagrange's equation to a mass small m in a potential V as a function of x, y, z. In spherical polar coordinates r, theta and phi, the units are dr, d theta and d phi, r sin theta d phi. So, their velocities are r dot, r into d theta by dt, r sin d phi by dt. Now, the kinetic energy becomes half m into brackets r dot square plus r square into brackets d theta by dt whole square plus sin square theta into d phi by dt whole square into r square. Now, the Lagrangian becomes L equal to 1 by 2 m into r dot square plus r square d theta by dt square plus r square sin square theta d phi by dt square minus potential V as a function of r theta phi. Lagrange's equations now become d by dt of dou L by dou q dot j minus dou L by dou q j is equal to 0, where j equal to 1, 2, 3 etc. n. The equations of motion for r coordinate is d of m r dot divided by dt minus m r into d theta by dt square plus sin square theta d phi by dt square plus the change in the potential dou v by dou r is equal to 0. The theta coordinate will become now d by dt of m r square d theta by dt minus m r square sin theta cos theta d phi by dt whole square plus dou v by dou theta is equal to 0. The phi coordinate now becomes d by dt of m r square sin square theta d phi by dt plus dou v by dou phi, that is equal to 0. All this for a central force. A central force is that one which is directed towards the center. For example, when we leave an object, it will fall down on earth. Wherever you do on the surface of the earth, it is directed towards the center of the earth. For such a central force, dou v by dou theta is equal to dou v by dou phi, that is equal to 0. So, there are no changes in the theta and phi coordinates. Change is only along the radius vector towards the center of the earth. The central potentials are also available in electrostatic cases, where if you take the positive charge and electron is being attracted towards that positive charge of the nucleus, such potentials are applied to atomic, molecular and subnuclear cases also.
మా కార్యక్రమాలపై మీ సూచనలు సలహాలు ఆహ్వానిస్తున్నాం. మీ సూచనలు సలహాలు మాకు తెలియచేయవలసిన చిరునామా: డైరెక్టర్, ఆడియో విజువల్ ప్రొడక్షన్ అండ్ రీసెర్చ్ సెంటర్, డాక్టర్ బిఆర్ అంబేద్కర్ ఓపెన్ యూనివర్సిటీ, ప్రొఫెసర్ జి రామరెడ్డి మార్గ్, రోడ్ నంబర్ 46, జూబ్లీ హిల్స్, హైదరాబాద్ 500033.